pass around the sign-in sheet. So yesterday I was talking about Piazza, the online discussion forum we have set up for Calc 1. Does anyone use it yet? Has anyone posted to it? There's been a couple people posted to it, and I just kind of wanted to show you it's beneficial if everyone in Calc 1 uses it, and I think you'll see if more people start using it. So that first week of classes, I sent out an email inviting you guys to it, but you probably didn't know what it was. If you search for it in your email, you should have that link. If you need another email, I can re-invite people. And if you haven't registered by the end of this week, I'll probably just send out another one to re-invite you to it. You're not forced to use it. You don't have to use it. But I think it could be beneficial. And if you look, someone had posted a question on the review homework that I assigned in Wiley. And it says, has anyone looked at section .4, question 14? I'm not entirely sure what it's even asking. And this is the one that had to do with asking for the cosine of tangent inverse of x. So another student had responded with explaining how to answer this problem, and their explanation was correct, so I went ahead and marked that as an instructor. You can trust this person's response. And then I put in the picture, so some of you might not have known exactly what that problem was, but looking at the picture you could recall that. And then I kind of try to explain it just one extra step. If you look, the online or the Wiley homework had to do with the difference quotient using this W and X. I think we talked about this one in class. And how to deal with that, and some of the students. And one of the other calculus instructor had answered that too. So I tried to give you a hint, and then he gave you a hint, and then as the students, they can reply to this discussion, like, oh, I still don't get it, or can anyone help me, kind of things like that. I put tutoring information on there. So we have the Math and Science Tutoring Center in the third floor of the library, and then we also have the Math Success Lab that's going to be starting in February. So it hasn't started yet, but this is the information for that. So if you forget that, you can find it here. You can also find it in Blackboard and other places. But this is going to be nice as we get closer to exams. If you want to study together with students in other sections, you can post, like, going to be studying at the library at 7 o'clock if anyone wants to meet me there. And you can kind of collaborate and explain things in that manner. So it's nice. It has some nice inputs. I think you can take screenshots and just copy and paste it in there really easy. Oh, this one.
So number 16, part E, we talked about how the solution and the answers were wrong. And so I repost about how to find average velocity. So if we want to find the average velocity of the function 2 sine of t, we want to set that equal to 0, you can put in this math type. So instead of, 3x caret 2, if you want to put in like a polynomial 3x squared, sometimes that's hard to read. So if you went to a new post, it has this, it's LaTeX, which not that anyone necessarily knows how to write in that way, but they give you these buttons that you can put. So if you want to put a fraction, you just put on the fraction button. If you want an integral sign or a derivative sign, partial derivative sign, as we get closer to using some of these, it might be useful to explain your question. You can also take a screenshot of the book or a screenshot of Wiley and post your question in there as well. So it gives you the notation, and then you could just put, okay, I want A over B. And then it shows you, or A over B, and it shows you what that would look like. And then you can insert that, and you can talk all you want about it. So hopefully, if you do, this is a good interface. The other instructors are looking at it as well as myself. So if you post something, you'll probably more likely get a response that all the students can see versus 15 or 16 emails to myself about number 14 on Wiley type thing. So I can just post the answer once. Did everyone get the sign-in sheet? The side? Sometimes the side of the room was. Maybe I need to start it over there. Okay. Also on Wiley, I had some students had some issues registering at a decent time last week, so I went ahead and pushed back homework 1.1 in the review to Wednesday at 11 p.m. So if you didn't have a chance to submit anything on those problems, you can still work on it for full credit, 100%, until Wednesday night.
All right, so we left off, we finished 1.2, now we're going to cover 1.3. Just want to make a note here. Quiz number 2 will be Thursday, so this Thursday it's going to cover 1.1, 1.2, and 1.3. So the intuitive approaches to the limits at A, and then 1.3 is limits at infinity. In college algebra and pre-calculus, you talked about this as the end behavior of a function, which you use to graph when you talked about the end behavior of a function, if it had a horizontal asymptote or not. So when you talked about graphing polynomials or graphing rational expressions, you could talk about, is it going to tend to infinity? Is it going to tend to minus infinity? Is it going to have a horizontal asymptote? Things like that. So we'll be approaching that more in a calculus sense, but you can recall some of the things you learned in college algebra and pre-calculus to see how that works. So we've looked at this function multiple times, this 1 over x. We talked about the limit as x goes to 0 from the left and 0 from the right of this function. And now we're going to look at the limit as x goes to infinity of 1 over x. 1.2, the introduction, was the intuitive approach. Look at the graph and kind of see what's going on. So if I take x getting larger and larger, then I have 1 over a number that's getting larger and larger. 1 over a number that's getting larger and larger, the whole expression is getting smaller, right? 1 over 5, 1 over 10, 1 over 100, 1 over 1,000, that's getting smaller and smaller. So this whole expression is going to 0. And it turns out we don't care if x is positive or negative. 1 over something getting really large, negative infinity or positive infinity, let me rewrite that, x goes to minus infinity is also going to go to 0. So 1 over a number, or a constant, let's say c, over something getting larger goes to 0. Just like we talked over, a constant over something getting smaller goes to plus or minus infinity depending on if it's going to 0 from the left or the right and if the constant is positive or not. So this is the generalizes 1 over, or a constant over something getting larger gets smaller. So that is going to go to 0. So we have the theorems from the book that you could print off here, and this is, instead of taking the time to write them, I just kind of want to explain them. This would be a horizontal asymptote. The notation, the limit as x goes to infinity of a function equal L, what that means is the function is approaching this value L as x is going to infinity. And of course, the exact same as x is going to minus infinity. So you can see how that is written here. If x is going to infinity, positive or negative, you don't have to have positive infinity. If the answer is positive infinity, you can write infinity. But if the answer is minus infinity, you need that minus infinity. So Wiley will accept positive infinity as well as just infinity. So similar things. Your book also gives you some information about some general graphs. And we're going to look at the graph of these functions to see how they work. And then we're going to apply them into a little bit more complicated functions. And you're going to have to keep in mind, the natural log function. Visualize that graph as x goes to positive infinity, it's going to go to positive infinity. Natural log, what's the domain of ln of x? 0 to infinity. So it would not make any sense at all to talk about the limit as x goes to minus infinity of ln of x. You'll never see that. If you do, it's a typo or an error or something. Because if you look at the graph of ln of x and the graph of e to the x, let's look at these two. So y equals ln of x looks like this, right? I'd only ever talk about the limit as x goes to infinity of ln of x goes to infinity. I might talk about the limit as x goes to 0 from the right of ln of x, and that goes to minus infinity. But it would not make any sense to talk about the limit as x goes to minus infinity of ln of x, right? Because I can't plug in ln of -5. You do that in your calculator, it'll say domain error. So it just wouldn't make sense to talk about x going to minus infinity. If we look at the graph of e to the x, we could talk about the limit as x goes to infinity of e to the x. What does that go to? Infinity. And the limit as x goes to minus infinity of e to the x? Zero, exactly. Okay, if I look at the graph, clearly I can see if I follow this graph as x is getting larger and larger negative, it's approaching 0, but it never hits 0. So we have a horizontal asymptote y equals 0 here in terms of x going to minus infinity. So we need to know how to deal with these functions when I mix them up into algebraic expressions. So let's look at an example. Let's talk about the limit as x goes to 0 from the left of e to the 7 over x. So this might look like, okay, there's a lot going on here. But this e is just a number, right? E is just a number. I can pull this e out and then take the limit as x goes to 0 from the left of 7 over x. So however this acts, if it's going to go to 0 or infinity or minus infinity, I can think of e to that power and then look at the graph. So do you guys recall what the limit as 7 over x as x goes to 0 from the left is? Negative infinity? Anyone? Someone says positive infinity? So I'm on the left side of 0, right? The left side of 0, all my numbers that I'm inputting are negative. So I'm inputting numbers that are smaller and smaller, but they're still negative. So if you think of 7 over a half, that's 14. 7 over a fifth, it's getting larger, right? But it's still going to be negative because it's 7 over minus a half. 7 over minus a fifth, right? So this whole expression is getting larger, but it's getting larger and it's always going to be negative. So this is going to act like e to the minus infinity. What does e to the minus infinity go to? It goes to 0, right? Did someone have a question on e to the minus infinity or negative infinity? Is this just the way I said it?
No, I was trying to answer, but that's wrong.
Oh, okay. Well, does that make sense? How you need to know how e to the x and this ln of x work, but maybe in a more sense of how a polynomial is going to work around it. Question? Okay, so remember the graph of 1 over x we talked about up here? And if I have x is approaching 0 from the left, this graph is getting larger and larger. So sometimes you can picture the graph in your head and see what's going on. But the concept, you should, at this point, have an idea of a constant over something going to 0 is going to go to infinity. And then if it's on the right or the left and the constant's positive or negative, you need to take that into account if it's going to be plus infinity or minus infinity. Question?
Get from the limit of x as it approaches 0 from the left, 7 over x to the second one.
How did I get from here to here?
Yeah.
Okay, so this e is, this is a function, right? E to the 7 over x. This e is not really part of the limit per se. E is going to go to some power. What is this power going to? So e to some power. The limit as x goes to 0, e stays the same, right? It's not if x isn't affected, but the power is potentially changing. The power is going to minus infinity. So what would e to the minus infinity go to? Well, that would go to 0.
But from the left, it's just that as it approaches it from the left, that's what's throwing me off.
Okay, so remember when we talked about right side limits and left side limits? It turns out this limit would not exist at x approaches 0. Right? Because the limit on the left and the limit on the right don't equal each other. So the limit's not going to exist. So here, I would only be able to talk about it on the left or the right. If this was the limit as x goes to 0 on the right, this would be e to the positive infinity, and your answer would be positive infinity. Does that make sense? Are you thrown off on the notation or the concept?
I thought that was from the left, so I thought that was going.
It's on the left side of it.
on the left side.
Yeah. And the plus is on the right side of it. Does that clarify some stuff? Yeah.
So polynomials with E is always going to be the power when you have all that pretty much.
Yeah, more than likely. Yeah. So you're going to have e to a power, and this power might be a fraction, it might be a polynomial, but you're going to deal with how this limit affects this power, and then you have e to either something going to 0, going to infinity, or minus infinity.
So if the minus infinity doesn't mean like a number, like 5,
This is mean the power is going to minus infinity. So if I'm plugging in e to numbers that are getting larger and larger and larger, this whole thing, negative larger and larger and larger. So if I plug in e to the minus 500, e to the minus 10,000, that whole expression is going to go to 0. What is this expression, or what is this function tending to as x tends to 0 from the left? Because I can't begin to graph this function, right? Potentially. Graphing it's not going to be too fun without a graphing calculator. So I have to say, okay, how is the power acting? The power is acting as going to minus infinity. So e to the minus infinity goes to 0. And you can confirm that by looking at the graph of e to the x, or e to a power. So if I just look at an example, the limit as x goes to infinity of e to the minus x, what would that go to? Good. It's saying the same thing, right? E to a power, and that power is going to minus infinity. You know, your book could get creative by taking the limit of minus infinity e to the minus x. What would our limit be there? It'd be 0?
there's two positives.
Well, there's two negatives, right?
Or
To
else
make a
two
positive.
negatives,
Yeah,
so it's-
right. So my x is going to minus infinity, and I have e to the minus minus infinity, so that's going to act like e to the infinity, right? So I have e to the minus minus infinity, which would act like e to the infinity, which would act like infinity.
Did you say on the first movement, if x was going to 0 and right, it would be e to the positive infinity equal positive infinity?
Correct. Good.
On this graph.
On this example, if I did this
Because of
same
this.
example with
Yeah.
x going to 0 from the right, then this 7 over x as x goes to 0 from the right would be just infinity. And e to the infinity goes to infinity.
Right.
So getting those concepts of how e works is important, because it's not going to necessarily always be just this e to the x you have to deal with. Okay, so the next thing I want to talk about is polynomials. So just like in 1.2, polynomials are about the easiest thing to take a limit of. And the same thing is true when we take the limit at plus and minus infinity. So let's look at limits of polynomials. And we're going to focus on the end behavior. The end behavior is going to act like it's going to match the end behavior of the highest degree term. So it doesn't matter how long my polynomial is, I'm only going to care about the highest degree term and then see how that interacts. So let's recall some things from college algebra and pre-calculus. Let's say I have this polynomial. I'm going to name it p of x. I'm going to call it, how do I want to write this? I'll say a x to the m plus bx to the m minus 1 plus cx to the m minus 2 dot 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 plus c naught. Some constant at the end, right? Polynomial. So this is a general polynomial. Let's say if a is positive and m is even. So this would be a polynomial where the highest degree term, so m's the highest degree term, is even and the coefficient is positive. So if you think of like x squared, x to the 4th, x to the 68th plus negative 7x squared, any long polynomial that if we look at the highest degree term, if you recall, the end behavior, when you talked about graphing, would look like this, right? You guys remember doing something like that in pre-calculus or college algebra? The end behavior, if I took infinity to the m power, or minus infinity to the m power, and m is even, I'm going to get infinity both ways. In the case where a is negative and m is still even, the end behavior is going to look like this. Right? We really don't know what it's doing in the middle, because the polynomial can have at most n minus 1 turnarounds. So it can turn around multiple times, but if it's negative, the limit as x goes to infinity and minus infinity is minus infinity. And we can look at if a is positive and m is odd, then we get the graph. You guys go ahead and continue on. Something like this. And if we think of the function x cubed, right, as x goes to infinity, infinity cubed goes to infinity, and minus infinity cubed goes to minus infinity. And then if a is negative, that flips over the x-axis. So if a is less than 0, pull this up some, and m is odd, we get this situation. Right, that end behavior, looking at the graph. So let's look at some examples. Take the limit as x goes to infinity of, let's say plus 3x to the 6th minus 2x to the 5th minus 17x cubed. So that theorem we talked about in the book, that, let's see, not the theorem, the statement, the end behavior, oh, we're not quite there about the rational expression. The end behavior is going to match the end behavior of the highest degree term. So if I let x get really, really large, even though I'm subtracting off an x to the 5th and an x cubed, it doesn't matter because x being really, really large, this x to the 6th overpowers these other terms. So I only care about how this highest power term is going to react. So to simplify this, I have this equals the limit as x goes to infinity of something like 3x to the 6th, which would be 3 infinity to the 6th power, which turns out to be infinity. If I look at this as x goes to minus infinity, I would have minus infinity to the 6th power, which would still be positive infinity, right? So my answer is still going to be positive infinity. Does that make sense? So it doesn't matter how long your polynomial is, you're only going to look at the highest degree term. And you need to also look at the coefficient in the highest degree term. That's important.
Yeah, because the coefficient like bears the sign positive or negative.
Yeah.
But then if the exponent is even or odd, that also affects it.
Correct. That's two things that you need to make an account.
Each other out.
They can sometimes with the negatives. Like, let's do an example where they would potentially cancel each other out. So if I take, I think I'm going to run out of room there, so let's just go down here. If I take the limit as x goes to minus infinity of minus 3x cubed plus 2x squared plus x plus 1. So we only care about the highest degree term, so I could rewrite this. The limit is going to act like the limit as x goes to minus infinity of minus 3x cubed. I have minus 3 minus, because I'm plugging in minus infinity for x, and that's cubed, right? So minus infinity cubed is minus infinity, right? So I have this minus 3, and then I have minus infinity, which minus 3 times minus infinity is positive infinity. Does that make sense? Remember we said that we need to keep in mind this limit? You need the limit until you actually take the limit. So at this point, I plugged in minus infinity for x. So I took the limit. I could drop that limit sign. Make sense? Pretty straightforward. You have different really there's 4 cases. Even power, positive negative coefficient, odd power, positive negative coefficient. You know how to deal with that. Okay, so let's look at limits of rational expressions. Question?
What would be the instruction for problem like that? I would solve for this, solve for that. Like,
Calculate the limit, evaluate the limit.
okay.
So you'd be given this information, say, yeah, evaluate the limit. But that's always a good, sometimes I don't write the whole expression or the whole question down, but yeah, I will say evaluate this limit. Question?
So like if the power on the minus infinity is even to the positive?
Yes.
Negative.
Yeah, so if this was negative infinity to the 4th power, it would just be infinity, right? Because it would be really negative 1 to the 4th power times infinity to the 4th power. So yeah, you have to be careful with this negative is not part of the x, but when you plug in minus infinity, it is part of the x. So the whole thing is cubed. Negative infinity to the cubed is negative infinity, but negative infinity to the 4th power would be infinity. Okay, let's see where I'm at. Let's look at rational functions. As x goes to plus or minus infinity. Rational functions are going to be very similar. A rational function is when you have a polynomial divided by a polynomial. So let's say f of x equals p of x over q of x. Our method here is going to divide each term by the highest power of x in the denominator. There's a quick method. The quick method is to take the in behavior of the highest power of term in the numerator, divide that by the in behavior of the highest power of term in the denominator. So I'll write this out. So the in behavior is going to match, is going to okay, so what this says is the in behavior matches the in behavior of the highest degree term in the numerator divided by the in behavior, or divided by the highest degree term in the denominator. So we can take, okay, what is the highest term in the numerator? What is the highest term in the denominator? Take that quotient and then simplify that quotient and then evaluate the limit. So let's look at some examples. This method, divide each term by the highest power of x in the denominator, is going to be helpful in some instances when we have maybe the square root of x to a power. So let's look at some functions. Okay, so let's take the limit. The limit as x goes to minus infinity of 4x squared minus x over 2x cubed minus 5. So if we look at the quick method your book talks about, it's going to say pick the highest power of x in the numerator and the highest power of x in the denominator. And the limit is going to equal the quotient of those two. So now I can simplify one more and take the limit as x goes to minus infinity. What's 4x squared over 2x cubed? 2 over x, very good. Does this function look similar to a function we've been talking about the last couple of days? So, what is the limit as x goes to minus infinity of 2 over x? 0. Good. So do you guys remember in college algebra pre-calculus when you talked about horizontal asymptotes? Horizontal asymptotes are very similar to the end behavior of a function, right? And pre-calculus or college algebra, you might have had something like a x to the m plus b x to the m minus 1 dot 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 over bx to the n. I don't quite remember the notation the book used, but let's call this a1 and a2. I think this will be, and this would be b1, b2, x to the n minus 1. And then we talked about horizontal asymptotes. And if m equals n, we had a horizontal asymptote at y equals a over b, right? Because the highest degree terms are going to cancel and you're going to have a over b. If m was greater than n, did you have a horizontal asymptote? Right? You didn't have one. And if n was greater than m, did you have a horizontal asymptote? Yeah, very good. You're going to see the same thing is going to happen with the end behavior of the function. If I take the limit as x goes to infinity of, let's say, x squared plus 1 over x, this is going to act like the limit as x goes to infinity of x, right? Which would go to infinity. But if I take the limit as x goes to infinity of x over x squared plus 1, this is going to act like the limit as x goes to infinity of 1 over x, which would be 0. In the last example, the limit as x goes to infinity, let's say 5x squared plus 1 over 3x squared, is going to equal the limit as x goes to infinity of 5 over 3, which would be 5 over 3. So you see those three cases again. This is the calculus approach to it. The limit as x goes to infinity. The limit as x goes to minus infinity, you can still use the same technique, except then you have to evaluate if the x is minus infinity and then the power of simplifying the polynomial. Any questions on that? Let's look at something to be careful about. If I take the limit as x goes to infinity, 5x cubed minus 2x squared plus 1 over 1 minus x cubed, your book teaches this method to divide through by the highest power of x in the denominator. So if I do that, the limit as x goes to infinity would be 5x cubed minus 2x squared plus 1 divided by x. Right. So the first method, divide by the highest power of x in the denominator. The highest power of x in the denominator is x. So divide top and bottom by x. So now I need to simplify this expression, simplify this expression. I'm getting some weird feedback with my recording device. So. Okay, so I have the limit as x goes to infinity. I would have 5x squared minus 2 plus 1 over x divided by 1 over x minus 3. So the limit as x goes to infinity, oh, sorry, yeah.
Be minus 2x?
I'm sorry?
Be minus 2x?
Yes, it would be, thank you. Because I have x squared over x, so I have one left there. here. Your book talks about the method of the highest power of x in the denominator. So I'm going to take the highest power of x in the denominator, which is just x. So if I divide top and bottom by that, and I take the limit as x goes to infinity, then this goes, 1 over x goes to 0, 1 over x goes to 0. I'm left with infinity over some negative 3. And since what did I want to... so you can apply this method, but be careful that you don't try to divide by the highest power of x in the numerator. So this is saying do not take the limit as x goes to infinity. So here we would have infinity over minus 3, which would go to minus infinity. If you took the highest power of x in the denominator, if you had something like 5 minus 2 over x plus 1 over x cubed divided by 1 over x cubed minus 3 over x squared, this is a problem. So your book, this is an example of this, be careful in your book. You can divide by the highest power of x in the denominator, that's perfectly fine. But do not divide by the highest power of x in the numerator, because that's going to lead you to this is going to 0, this is going to 0, this is going to 0, and this is going to 0, and that's going to make you think the answer is 5. The answer is not 5. Do you guys see that? Here, this is going to infinity, so we take the highest term here, this goes to infinity, this goes to minus 3, so our answer is minus infinity. But if I divide top and bottom by the highest power of x in the numerator, I get this expression, right? 5 minus 2 over x plus 1 over x cubed divided by 1 over x cubed minus 3 over x squared. Oh, sorry, these would all be going to 0 then. So you'd have 5 over something going to 0, 0, and this is just going to lead you down the wrong path. Generally, this is an issue because students like the quick way. They like to take the highest power of x in the numerator, the highest power of x in the denominator, and go from there. So I want to look at a graph of a couple more common functions and talk about their limit. So let's look at tangent inverse. If I was to take the limit as x goes to infinity of tangent inverse of x, what would that approach? Well, let's look at the graph. We call the graph of tangent inverse. It has a horizontal asymptote at minus pi over 2 and pi over 2. So what's the limit as x goes to infinity of tangent inverse of x? Pi over 2. What would be the limit as x goes to minus infinity of tangent inverse? Minus pi over 2. So now dealing with tangent inverse just like we did with e to the x. One plus 1 over x to the x power. Let's look at this graph. Does this look familiar? Let's see if I can graph it correctly. Does anyone know this horizontal asymptote? If I take the limit as x goes to infinity, what is this function going to approach? E. Good. So this is e. This is used in some proofs later on when we talk about definition of a derivative. So you might see this function, but the limit as x goes to infinity of 1 plus 1 over x to the x power goes to e. And the same thing with the limit as x goes to minus infinity of 1 plus 1 over x to the x power. By definition, this is e. 3.14, not 3.14, that's pi. 2 point something, that relationship. So those might come up. Let's look at an example that's on Wiley. If I want to evaluate the limit as x going to infinity of the square root of x to x to the 6th plus 5 minus x cubed. So if I take x to go to infinity, square root of infinity to the 6th power, that's going to infinity. minus infinity, because really x to the sixth, the square root of that would be x to the third, right? So I have like x to something going to x to the third minus x to the third. So I really don't know what's going on here. Your approach on this one is to multiply top and bottom and make it a rational expression. Divide by the highest power of x in the denominator and go from there. So if I multiply x to the sixth plus 5 plus x cubed, by doing this I don't exchange the expression because I'm multiplying by 1. So I have the limit as x goes to infinity, x to the 6th plus 5 minus x to the 6th. Right? The whole point of picking this number is so that the middle two terms cancel. Right? So I have this expression times this expression, the middle two terms cancel, this expression times this expression. So minus x to the 6th. And then my denominator, I have the limit as x goes to infinity of 5 on top all right, 5 on top, and then on bottom x to the 6th plus 5 plus x cubed. So here, if I divide top and bottom by the highest power of x in my denominator, my highest power of x in my denominator is x cubed. Does anyone know what the answer would be here by using a constant over something? Because now it's not infinity minus infinity, it's infinity plus infinity. So if I have 5 over infinity plus infinity, I really have 5 over something going to infinity, right?
0.
Which would go to 0. And you can make that conclusion at this point. You can also divide top and bottom by the highest power of x. It's going to get you to the same conclusion there. All right, so let's look at some Wiley problems. Next. So if you go to your view, if you look at 1.3, so let's look at this function, and the question is, let's go to full screen. So what is the limit of this function as x goes to minus infinity? So x is going to minus infinity, x is the input, so if you take x to go to minus infinity, what's this approaching? It's approaching 1. What about the limit as x going to positive infinity? 0. Keep in mind that these are randomly generated, so if you go and log into yours, your graph might be different. So, explain that? Okay, so the limit of this function, so this is the intuitive approach, if you look at the graph, x going to minus infinity, here I'm plugging in numbers that are getting larger and larger and larger. So what is my output going to? Okay, so and then you see that as x is getting larger and larger, the graph is approaching 0. This problem is using the theorems we talked about in 1.2, how to add the limits of functions. So the limit of a sum of function is a sum of their limits type thing. So that gives you 2 of them and expects you to plug that in. So that's pretty straightforward. The limit as x goes to minus infinity. So if I look at the highest power of term, if I look at the highest term in the numerator and denominator, and I simplify that, what am I left with? 8 over x, which is very similar to the function that we've seen before of a constant over x, right? And as x goes to minus infinity, 8 over x is going to go to 0. So this whole thing goes to 0. In this expression, you're going to divide, let's look at this one. You're going to divide top and bottom by the highest power of x in the denominator, But it turns out the highest power of x in the denominator, there's a tricky way we can rewrite this. So let's look, this is like number 26 on Wiley. So we have the limit, and as soon as I write this, I'll switch over. The limit as x goes to infinity of the square root of 7x squared minus 12 divided by x plus 6. So the limit as x goes to infinity of the square root of 7x squared minus 12 divided by x plus 6 divided by x. Okay, so I have to divide by the highest power of x in the denominator, but I can be tricky the way I pick x to look like. So I'm going to make this the absolute value of x. And the key in this example is the absolute value of x can be replaced with the square root of x squared. And then here's something to keep in mind. The absolute value of x can be replaced with simply x without any problem if x is going to positive infinity. If x is going to minus infinity, I need to replace the absolute value of x with minus x. So I'm going to rewrite this. The limit as x goes to infinity of the square root of 7x squared minus 12 divided by x squared over 1 plus 6 over x. So I just simplified that. Since x is going to infinity, I can replace the absolute value of x with x. And so I have x over x plus 6 over x. So I need to simplify my numerator, get the limit as x goes to infinity of the square root of 7 minus 12 over x squared divided by 1 plus 6 over x. So I could replace this absolute value of x with the square root of x squared. The absolute value of x will always equal the square root of x squared. But the absolute value of x really picks up. The absolute value of x can be replaced with x if x is positive. If x is going to infinity, I can replace it. But the absolute value of x is going to have to be replaced with minus x if x is going to minus infinity. If you think about this, negative 5. The square root of negative 5 squared is 25, and the square root of that would be 5. But my x was negative 5, so I just take the absolute value of negative 5, which would be 5. So the right side equals the left side. Here, if I take 100, the absolute value of 100 is 100. But if I take negative 100, is x. So negative 100 is x. So the square, or the absolute value of negative 100 would have to be the negative 100 to be 100, right? The absolute value of negative 100 is 100. So I have to replace the absolute value of x with minus x when x is going to minus infinity. So that's something that you have to be careful with. We'll do the same example with x going to minus infinity in a minute. If we have time. Question?
So when you're saying x is going to minus infinity, you're talking about the limit?
Yes. Because this function is, doing some funky things. It's not even defined at x equals minus 6. But we don't care about anywhere in the middle. We only care about the extremes. When x is going really, really large negative or really, really positive, large positive. So we don't care about anything other than that. So in this case, I can replace absolute value of x with x because I know x is going to be positive. Here I have to replace the absolute value of x with minus x because I know x is negative. So negative 100 is a positive 100, and that equals the absolute value of negative 100, if that makes sense. Okay, so in this instance, I can apply the limit. I have the square root of 7 minus 0 over 1 plus 0, which gives me the square root of 7.
Anything divided by infinity?
A constant over something going to infinity goes to 0. It doesn't matter if it's x to the 100, if it's 7 over x to the 100, that's going to go to 2.
I've got to ask.
Question?
It was back on what you had written. I'm trying to follow the steps that you use, and on the bottom left there. Yeah.
Yeah?
In the first term where it's the square root of 7x squared minus 12, should that be divided by x? Why is that divided by x squared?
Because I replace this absolute value of x, I replace that with the square root of x squared.
Okay.
So then I can put it in under the square root.
But then you use only x.
I only, in the absolute value of x equals the square root of x squared. They're the same thing. So I divided by top and bottom by the same thing. I just rewrote it conveniently here to put it in the square root, and I don't need a square root here, so I just left it as x. All right, I'll see you guys tomorrow, and we'll finish this last bit, and then we'll talk about 1.5.
What are your responses?